Hello everyone, it's Nono and Aziz here. We are today recording in person from Seville.
Happy to be here in Sevilla with you.
And we bring you one new episode of the Bytes series in which we're going to be talking about the black box. Hey, it's Nono, and this is the Getting Simple podcast.
So this is Aziz here, and today's episode is going to be titled The Black Box. This is a topic Nono and I often discuss, and it's about the abstraction of technology and the way that it's packaged to us in such a fashion that most of us have no clue of what we're doing and how it's taking place, but we're just interested in the final result and we're happy and content with that. But as soon as problems arise, as soon as we have to troubleshoot something, then we have to dig into how the process works and how can we fix the issues that we're facing.
And I guess what we want to do today is to try to see how we got to where we are, right? Like what ancient technologies or what was there before software and how we got to the situation in which we are today with all of these apps and online systems working for us that we don't know anything of.
Right, because we're so dependent on this technology. We're in a very particular moment in time where we're interacting with all these technologies around us that most of us have very little understandings of how they work and how they process things. But that hasn't always been the case, right? Like probably our grandparents were interacting with very mechanical technologies where the process and the actions that took place were very visible in front of them. For example, windmills or the bicycle, or even things a little bit more complex, not just these simple machines and technologies of their time, but even older technologies, perhaps way older than our grandparents, such as the Pascaline calculator, which was invented in the 17th century, and it was quite a popular machine, in fact, and it was capable of doing simple tasks like adding and subtracting and even multiplying. That technology was kind of seen as an early version of the computer, but it was also very mechanical, and so whoever was inputting was performing a physical action, inputting his parameters, let's say, and it went through the machinery. It was quite visible. The gears would turn, the system would move, and it would output a result. And so that whole process was quite visible and there for the user to see and observe and learn from.
And I think the problem that we have today with computer software, which is abstractions, right? We have high-level programming languages that express mathematical functions or things, but they get executed by the machine in like really low-level languages that we don't even understand. And also many times those abstractions wrap a lot of knowledge that we give for granted or that the machine takes care for us, right? So that was present, I think, on mechanical devices. For example, if you think of a tiny engine that is making something rotate, right? You don't really care anymore about the inner workings of that engine when you buy it, just what you're getting out of it.
Exactly. The result of the rotation is right now all you're interested in. There's no need for further understandings. And I think, this is definitely what happened during the electronic age, right? We moved from mechanical computing to electronic computing, which of course has great benefits. There's no longer the same amount of wear and tear and the breakage of machines. They're more reliable and faster. But during this transition, we've lost sort of connection to the way computing is handled and the observation of that computing.
Yeah, and I think you also mentioned in a previous conversation, Aziz, that we also have lost the visibility and some sort of democratic access to how mechanisms work, right? Because you can tear apart the machine and you can see it. Even if it's proprietary, you can break it and you can see the components inside. But with software, this is really different because you can, many times you can't decompile algorithms that are proprietary. And in many cases, or most cases, it's even illegal to try to do it.
Sure. I mean, again, comparing to previous technology, they would have been protected by a patent. So you couldn't exactly replicate them, but you could at least gain a lot from the knowledge by simply just observing how they function. In modern day, we don't have access to that, right? Things are either encrypted or highly illegal to decompile. So that leaves us in the dark with the way we operate. Yeah.
And I think today we can compare that visibility of mechanical devices to open source software, because even if the algorithms are super complex, we have access to them. And if we have enough time and interest, we could dive into how they work and try to understand them. But many of them are not so open.
Right. And I think even with that, we end up still always standing on the shoulders of giants, right? Because the way that modern or electronic computing works is it's always binary. It's always ones and zeros, which isn't, in fact, human readable. And very few people will ever interact with that binary code. And so you and I are quite comfortable with coding. And I'm, for example, I work great with C#, but in fact, I really have no idea how C# works behind the scenes. So I'm still dealing with a very high level of abstraction. And therefore, I'm limited in what I can do with it.
We should make an episode talking about programming languages.
For sure, yeah.
So I think we can say computers excel at making repetitive and complex tasks automatic. We can see in our daily lives the advantages of that level of abstraction, where we can not even use programming languages or code, but applications that have been made for us that are executing many, many different functions behind the scenes, and we don't even care about them, right? I recently listened to an interview in which Travis Oliphant, when he's talking to Lex Fridman, mentions how programming enables these abstractions we're talking about. And he explicitly says that abstractions are powerful in that we can now quickly make bigger and higher level things on top of them. But they're also dangerous because they limit us to the things we may be left behind in producing those abstractions, right? So this talks about who's making the programs or the algorithms that we use daily, and what happens if there's some bugs or some errors in the code. I was talking to Aziz before, and one of the things that came to mind is maybe you don't care that much about the algorithm that is enhancing your photos on your iPhone or your device, but what about the algorithm that your bank uses to tell you if you can get a loan, or maybe the exchange rates that your money is getting converted from one to another? These are things that, we still don't know anything about either way, because those algorithms might be closed sourced, or maybe just the bank or whoever the exchange is don't want to share them with you. So I think this is where even people who don't care about the algorithms underlying them have conflicted interests, right? Because it's going to affect your daily life.
Sure. I mean, yeah, exactly. Our whole lives are currently run by these background algorithms, and very few of us have any idea how they work, if they're even reliable, if we should invest and trust these software and these machines so much with almost our entire lives, right? What happens if an outage occurs? What happens if things go wrong? Do we have a backup plan? Very few of us know. We're just blindly trusting these black boxes. This is, I guess, what scares most people out of crypto. If the process was more democratic and visible to most, I feel like a lot more would be investing, and some are very comfortable in taking this leap of faith.
I guess because we were initially talking about the black box, we're now talking about abstraction. And abstraction doesn't necessarily mean black boxing something, right? Black boxing in high level terms is when there's something that is being executed, something that's happening, but you don't understand it. You don't have a way to know what's happening. Logic abstraction means that we get something that is maybe a calculation or a process that we're doing over and over again, and we turn it into a function that we can reuse. That doesn't mean it's a black box. We can have a function. So I'm thinking of, for instance, Python code. You can define a function that adds A and B, and the inner logic of the function is just going to say something like return A plus B. So every time you want to reuse that abstraction, so that function that adds A and B, you just say add A and B, and then you get the result. you can go back to that function and see it. You can see what it's doing. So you could have more complex algorithms like calculating the mean or the average of a set of numbers and stuff. And you can go back to it, read the code, and understand the logic. That's an open, transparent algorithm. It's visible to you and you can understand it. But many times those are closed, and that makes them a black box because you cannot see how things are calculated. But also they can be so complex, even if they're open, that it's impossible for you with your knowledge to understand them. So I guess there are two different set of black boxes, right? The ones that are black boxes because they're closed and we cannot see them, and the others that are because of the complexity of the processes that are going on, we don't have a way to understand them or make sense of them. And I think this is what happens with machine learning. When we have a function like a plus b, we have two parameters. But then if we go to a convolutional neural network or an image classification program, they can go up to having millions of parameters. And it's really hard to make sense of why they're learning what they're learning or why they're making, quote unquote, the decisions that they're making. There are techniques, right? There is an entire field of explainability to understand what neural networks and machine learning and artificial intelligence systems are doing. But, it's a science. You need to have a lot of knowledge. You need to have the methods. You need to have mathematical knowledge to be able to inspect what's going on. So I think as we move forward, right, we'll be relying more and more into these algorithms. So I guess we need systems to make them explainable to other people.
It's great to also see that a lot of people are starting to learn code these days, because specifically for reasons like the ones you mentioned, because our world is run by it and very little of us understand it. So we've ended up in this situation where things are very polarized, right? There's a select few that are capable, that somehow now end up with so much more power because of their access to these things, and a lot are left behind. And so definitely I think as a culture, we have to move towards a more democratic process and the evolution of these things. It's very difficult, of course, as we can imagine, since it's such a wide spectrum of knowledge that's required. But I think it's a necessary step that we have to collectively work towards.
What's commonly happening is that only the people who are developers or researchers or people who want to tinker and try to improve or use the code that other people are building for their own needs, other people just don't care about it and won't pay attention to how the code works or whether it's open or closed or whether it can be improved or if it's not working right. More and more, we're going to see places in which the actual inner workings of algorithms affect our daily lives, and other people are going to need to know how they're working and how they're using the information or how they're returning the outputs that they're returning when they feed these programs with an input, because they're going to be determining factors for them to make decisions in their day-to-day. We're going to have to find ways, we as in the people making the algorithms and people who are technical, to explain how these programs are making decisions for them.
I certainly look forward to that day. So I don't know about you, but it sounds like a future I want to be part of.
Thanks for listening. We'll see you next time.